Alright, so this is the third and final electrolysis video. It is probably the most important because it deals with the core practical, and the bulk of the electrolysis exam questions over the last few years have been on the electrolysis practical. So in the electrolysis practical, you always use the electrolyte copper sulfate, aqueous, but you electrolyze it using two different methods. One method, you're going to use inert electrodes, so electrodes that don't react, and this is similar to what we've seen in the previous videos. Then the other experiment, you're going to use copper as your electrodes, and that's what's going to change things. So we'll start with the inert electrodes, the ones that we've seen before. It'll just be a little recap from the second video, okay? So I've got it written out here, okay? This is my experimental setup. Panic, positive anode, negative is cathode. Copper sulfate aqueous is my electrolyte. So I've got copper ions and sulfate ions from the copper sulfate, and I've got H plus and OH minus ions from the aqueous. Turn on my battery, the copper ions and the hydrogen ions will be attracted to the negative cathode. The other two will go to the positive anode. And as always, only one product is going to form at each electrode. So at the cathode, you're looking at Cu2 plus and H plus and trying to decide which product will form. To do this, you use your reactivity series. If you look at your reactivity series, copper is lower than hydrogen. This means it's less reactive. This means it's more stable. So when we're doing electrolysis, we're going to form the product that is more stable. Copper is more stable than hydrogen. So those copper ions are going to be turned into copper metal. Those hydrogen ions will not be discharged. So if we have a look at what that's going to look like, we've seen this already. So they both migrate to the cathode, but the Cu2 plus is the one that gets discharged because the copper is less reactive than hydrogen. My half equation shows my Cu2 plus ions becoming Cu. Cu2 plus as an ion is aqueous, it's dissolved in solution, but as soon as they become copper again, copper metal is solid. For that to happen, they lost 2 electrons, give them back, and you're going to form a neutral copper again. Because they're gaining electrons, I can say it's reduction, but just notice what's being reduced. I can't say copper is reduced, I have to say the copper ions are reduced. Metals don't gain electrons, but metal ions can. You have to make that distinction. Because I'm forming copper solid, that's going to be deposited on the cathode. I'm going to see the cathode get bigger as a brown copper solid gets built up around the cathode. At the anode, we saw this as well last week, okay? The 2 ions that go there are OH minus and SO4 2 minus. Usually the rule is the halogen always forms, but in this case you don't have a halogen. And of the 2, it's the OH minus ion that's going to be discharged. This is the hardest half equation to write because you need to know your products. You've got oxygen and hydrogen, but you do form oxygen, you don't form hydrogen gas, you actually form water, and you form 2 molecules of water. So you would need to learn this equation. It did come up last year. If we look at what's happening, because you're forming oxygen gas, you are going to see bubbles. To test that it's definitely oxygen, insert a glowing splint, it will relight. So all of this is the same as what we saw last week. The only thing that's different is you can also be asked for another observation. And that observation relates to the colour. Now copper sulfate is this beautiful blue colour, and it's that blue colour because of the copper ions. The Cu2 plus ions give it the blue colour. If we look at what's happening here, at the cathode, those copper ions are being converted into copper metal. So as electrolysis takes place, you get a decrease in the number of copper ions because they're being converted to copper metal. That decrease in copper ions will cause the blue colour to fade. So as the concentration of Cu2 plus decreases, that blue colour will fade. Press pause, have a go at doing questions 1, 2 and 3. Try not to look back at your notes, try and do it from memory, and when you're marking it, just pay particular attention to your half equations, make sure you've got them the right way around. Alright, so question 1, I've already gone through it. These are the ions that migrate. Copper is the one that's discharged. There's my half equation. Pay attention to your state symbols. Cu2 plus is reduced. Don't say copper, it's Cu2 plus, and you're going to see a brown solid deposited. The anode, they're the 2 ions that will go there, but the OH minus is what's going to be discharged. That's your half equation. Specifically, it's the oxygen being oxidized. Don't say OH minus is oxidized. It's oxygen that's being oxidized, and because you're seeing producing a gas, you are going to see fizzing. What's going to happen to that colour? The blue colour will fade, and it's fading because of the Cu2 plus ions. You have to specify it's the Cu2 plus ions specifically that decrease. That's what's causing the fade in colour. Right, we are sticking with the same electrolyte, copper sulfate aqueous, but we are now moving from inert electrodes that don't react, to copper electrodes. And the reason we do this is we're trying to purify copper. Copper is useful, okay? We use it in electrical wires. And because it's useful, we need pure copper in large amounts. And you need a process that enables you to purify impure copper, and electrolysis does that. So you're going to have copper electrodes, but they're not going to be the same. One of those copper electrodes is going to be impure copper. So there is copper in there, but alongside impurities. And then the other copper electrode is just going to be pure copper, nothing else there at all. The first thing you need to do is to decide, do you put the pure copper at the cathode or the pure copper at the anode? Now if we look at what's happened in all of our electrolysis experiments, it's always the cathode that gets bigger. The positive metal ions move to the cathode, they become solid again, and the cathode grows in size. So if you look at these two, if you know the cathode is going to end up getting bigger, which one of these do you want more of at the end of the experiment? Well, we want more pure copper at the end of the experiment. We want the pure copper to get bigger. Therefore, we're going to put the pure copper at the cathode. That means the impure copper is going to go to the anode. So this is going to be my setup, okay? My anode is now going to be a piece of impure copper instead of a piece of graphite. My cathode is going to be a piece of pure copper instead of a piece of graphite. My electrolyte is exactly the same, copper sulfate aqueous. I've written oxidation and reduction next to the anode and the cathode because the same process happens at the electrode every single time. It doesn't matter what your electrolyte is, it doesn't matter what your electrodes are. The anode is always oxidation, so the 2 vowels go together. The cathode is always reduction, the 2 consonants go together. So first thing I'm going to do is describe what happens at the anode. We're going to start with the anode this time, okay? And if we look at what I've got at the anode, okay, because the anode is positive, the OH minus and the SO4 2 minus migrate there, but in this case we also have solid copper at the anode. Now I've never had to consider the electrode before. The electrode has always been inert. It's unreactive, it doesn't get involved. But in this case, because I do not have inert electrodes, the electrodes themselves come into play. I've got these 2 ions from my electrolyte, but I've also got solid copper metal. And now I'm choosing between 3 things. Which of these 3 things is going to be oxidized? It's always oxidation at the anode. Now of the 3, it's actually copper, the copper electrode, that gets oxidized. Remember, oxidation is loss of electrons. Metals lose electrons when they react. So what we're going to see here is that copper solid is going to lose 2 electrons to form a Cu2 plus ion. Now look how my state symbols change. When it's an atom, it's solid. As soon as it becomes an ion, it's aqueous. Okay, so those ions go into solution. All right, so specifically I can say that the copper is oxidized. The solid copper metal with no charge loses an electron, and they form these copper ions. Now what's going to happen to those copper ions when they form? Well, your copper ions are positively charged. They're going to be attracted to the negative cathode. So all of those copper ions are going to migrate across to that negative cathode. And that's going to cause the anode to decrease in size. All right, so all of your solids, you're just basically going to take lumps out of this. All of these copper atoms are going to become copper ions, and those copper ions are going to move across to the cathode. The anode's going to get smaller and smaller and smaller. It's going to shrink, and as it starts to fall apart, the impurities, remember it is impure copper, they all just fall to the bottom and they form what we call sludge. So the anode is going to decrease in size. All right, so that's the anode. What happens at the cathode? So if we consider what we've got at the cathode, we've got these Cu2 plus ions that are moving across. We've also got the Cu2 plus ions from the electrolyte. We've also got the H plus ions from the electrolyte. So you've got 3 positive ions all moving across, all right? But sorry, 2 of them are exactly the same, Cu2 plus. And then you've got the cathode itself, which we said is made of copper. So if we consider what we've got at the cathode, we've got the positive ions and then you've got solid metal. Which one of these is going to gain electrons? All right, so first of all, we'll consider the copper metal, okay, because that was the answer at the anode. But reduction is gain of electrons. Metals do not gain electrons. Metals lose electrons, sure, but metals don't gain electrons. So you cannot reduce the copper metal at the cathode. If you did, you'd end up with a Cu with a -2 charge. Metals don't have negative charges, so that's not going to work. So I'm back to looking at my Cu2 plus and my H plus, and as we saw before, it's the Cu2 plus that is preferentially discharged. So my half equation is the same as what it was in the last experiment. The Cu2 plus ions gain 2 electrons and become solid copper metal again. Again, it's the Cu2 plus that's being reduced. So what are we going to see happen to the cathode? Well, all of those copper ions move across, okay? The copper ions themselves do not make the cathode bigger, but when those copper ions get turned into copper metal, that's what makes the cathode get bigger. So we're going to see that cathode increase in size. It's going to get bigger and bigger. All right. So let's just, again, I know students get this wrong because I know the equations are really similar, but yet they're subtly different. All right. Look at the 2 different equations that I've got. Okay. At the anode, you're starting with a solid copper atom. You are oxidizing it to turn it into an ion. That ion can then go into solution and move. That ion moves the whole way across to the cathode, then it gets its electrons back, and then you end up with solid copper. So you've got solid copper in both equations, but on opposite sides. You've got copper ions in both equations, but on opposite sides. And you have to have that the right way around, or else you're just wrong. Again, when you're talking about what's being oxidized and reduced, you need to be really mindful. Here I can say copper is oxidized. You can write the word copper, you can write Cu. But when I'm talking about what's reduced, I would have to say a copper ion is reduced, or Cu2 plus. You leave out that 2 plus and you're just wrong. Okay, so you really have to make sure you're picking up on the subtleties of the differences here, and you've got it absolutely spot on. The other thing you're going to need to comment on is what happens to that blue colour. So we said copper sulfate is this blue colour. What happens? The blue colour is caused by the Cu2 plus ions. And if we look at our equations, you can see we're making Cu2 plus ions at the anode. So if we look at the anode in isolation, I would expect that blue colour to be getting darker, more pronounced, because of all of the Cu2 plus ions that we're making. But then when we consider the cathode, you can see that you're removing Cu2 plus ions from solution. You'd expect the blue colour to fade. These things don't happen in isolation. They're happening at exactly the same time. You're making Cu2 plus ions, but then you're also reducing Cu2 plus ions. Overall, the Cu2 plus ion concentration remains exactly the same. So overall, the blue colour remains exactly the same. I want you to press pause and have a go at doing these questions. Again, try not to look back. Try and do them for yourself. I want you to do question 4, 5, 6 and 9. In question 9 there's a mistake. I've asked you what happens to the colour using inert electrodes. It should be copper electrodes, so this experiment here. So 4, 5, 6 and 9, press pause, have a go. Alright, so 4, at the anode you are using your impure copper, at the cathode you're using your pure. Just remember the cathode always gets bigger, you want to end up with more pure copper at the end, so you're going to put the pure copper at the cathode, that leaves impure at the anode. Electrolyte is always copper sulfate, aqueous, alright? You wouldn't use a different electrolyte, because if you use, say, sodium chloride aqueous, then you're just introducing sodium ions into the equation, alright, which we don't want to do. So we want to make more copper, it makes sense to use an electrolyte that includes copper. Why is the mass of the anode going to decrease? These questions come up all of the time, alright? So I've asked you to use a half equation in your answer. So if we look at what's happening at the anode, it's not the OH minus and it's not the SO4 that are getting involved. It's the electrode itself. The solid copper at the electrode loses electrons and forms Cu2 plus ions. Those Cu2 plus ions then move over to the cathode, causing the anode to just fall apart. The impurities, because it's impure copper, just collect at the bottom atom as sludge. All right, so that's your half equation. Make sure your state symbols are correct. Make sure your charge is correct. You're starting with something neutral, you're turning it into something charged. What's happening at the cathode? This is the same as what we have seen before. So Cu2 plus gets reduced. When it gets reduced, it turns back into copper metal, and that copper metal builds up around the cathode. So you see this copper metal being deposited, and that copper metal makes an increase in size. So you get an increase in mass. Again, just double check your half equation, make sure you've written it the right way around. And then question 9, I asked you to do, I told you it was supposed to be for the copper electrodes. So in the copper electrodes, the blue color is going to remain the same. An equal number of Cu2 plus ions are being formed at the anode, so we're making them at the anode and then we're reducing them at the cathode. Don't say Cu2 plus ions are oxidized at the anode. That's not right. Copper is oxidized, okay, and when they're oxidized we form Cu2 plus ions. So again, language really matters here. I'm making Cu2 plus ions at the anode, but then I reduce them at the cathode. The overall concentration of Cu2 plus remains unchanged. There are a few other questions just relating to the practical itself, which I'm just going to run through with you now. So if we come up here and look at question 7, what should be done to the copper cathode before you start the electrolysis? So if we think about what we want to happen, you're trying to make more pure copper. So particularly at the cathode, that's where you're putting your pure copper. You want that piece of pure copper to be clean, and you want it to be nice and smooth so that the other copper can easily be deposited on it. In order to make something nice and smooth, all right, you're going to use like an emery board, you know, so the sort of thing that we use to file our nails. You're going to use an emery board to make it nice and smooth so that the copper can easily stick on during the electrolysis. You might also wash it, clean it to remove any impurities. You want it clean, you want it smooth before you start. And this is all before you start, okay? They can sometimes ask you what you do at the end before you determine its mass. So with the cathode, you might weigh it at the start and see it's got a mass of 2 grams. At the end, you weigh it again. That mass should have increased because you've added all of this extra copper. To make sure your mass is accurate, you're just going to give it a little rinse, all right? Rinse off anything that hasn't properly stuck. Give it a little rinse. Sometimes you just use water. Sometimes you can use propanone. That's the same solvent that you get in nail varnish. And because it's prop, we should know that it's got 3 carbons. Anone is a functional group we haven't actually studied, but it's an organic compound with 3 carbons, and you can use that to remove any grease or any impurities before you get the final mass. Now please take care, emery board is at the start to make it nice and smooth. You're not going to use an emery board at the end. If you start filing it with an emery board at the end, you're just going to knock off all of the copper that you've just added. So at the end you're going to be far more gentle. You're just going to give it a little rinse. Down here, state 3 ways you could increase the rate of copper production at the cathode. If you want to speed things up, there's a few things you can do. If you increase the concentration of copper sulfate, you've just got more copper ions in there. You can increase the current. Putting the electrodes closer together, just reducing the distance between them, makes it easier for that migration to occur. You can also say, something else you can say, oh, there is something else you can say. What else can you say? Oh, you can make the electrodes bigger, okay? If you increase the surface area of the electrodes, it's just a greater surface for the oxidation and the reduction to take place, and that's also going to speed it up. The last one, if you increase the current, why does that actually increase the rate of copper? Hopefully from physics you know that an increase in current is just increasing the flow of electrons, and if you've got more electrons you're going to be increasing the rate of reduction, which is going to speed up the process. You've got a few questions, exam questions to do based on this. These again, as I said, are the most common exam questions, so just pay very close attention to the mark scheme, see where you're picking your marks from. I would really advise you to learn how to write the half equations, because the half equations will pick up all of your marks. Even if you're not asked for them, get in the habit of writing them, and they will help you pick up the marks. Even if you stumble with your words, they can mop up any marks that you might have lost. So please just put the effort in, learn them, and practice, pay close attention to the mark scheme. All right, that is it.